All right, we are starting Unit 6 on thermochemistry. We're going to take a look at topics 1 through 3 as they kind of all go together and are pretty basic. We're going to look at endothermic versus exothermic, review energy diagrams, and what is called thermal equilibrium. So we will explain the relationship between experimental observations and energy changes associated with chemical or physical transformations, as well as represent them in energy diagrams. And we'll also explain how heat transfers and when it reaches thermal equilibrium. So let's first start and review endothermic and exothermic processes. So we've got a few pictures here, diagrams. So endothermic and exothermic processes can be either chemical or physical. So the first examples I give in each are physical changes. So for endothermic means energy is going into our system or into our substances. Our system is defined as the chemicals or objects that we are focusing on in our reaction or process. So, for instance, an ice cube melting, for that ice cube to melt, it has to gain heat from its environment, and therefore it is endothermic. It is taking in energy to melt that ice. And the energy is going in to separate and break some of the intermolecular forces. It won't break them all, but it'll break some up, and so the molecules can flow around each other. If we keep adding energy, we can see in the second picture there that eventually the water can start to boil and we start to get steam. So if we add in more energy into our system, into our water, then we can break all of the intermolecular forces between molecules, and those molecules can escape and separate, and we get a gas. So that's boiling. So melting and boiling, putting in energy to do those things, those are both endothermic processes. Now in a chemical reaction, it's not as obvious. We're not putting something on over a fire on a stove. An endothermic reaction is where it's pulling heat energy from the environment in order to break bonds in our reactants and form our products. So we have an overall energy change where our products have more energy stored than our reactants. So it needs that extra energy from its environment in order to make this work. So if we look at that, we can see the arrows going in. It's pulling the energy from everywhere. So if it's sitting on the table, it can pull energy from the table. If you put your hand on it, it can pull energy from your hand, from the air, anywhere around it. Now, exothermic processes give off energy. So what we sometimes don't think about is the opposite of endothermic. So exothermic, when we take water and it freezes into ice, like these icicles on this cabin, then that water has to give off its extra heat in order to freeze, in order to form the intermolecular forces to create that solid. So it is giving off its extra heat into the environment in order to solidify. And then our second picture there, we've got water condensing onto a piece of glass. So that gaseous water meets a cold surface and gives its extra energy, or loses its extra energy to that cold surface, and therefore turns into water condensation. So again, losing the extra energy in order to form intermolecular forces, allow those molecules to stick to each other more and create that water, that condensation. And then we got our chemical reaction. So reactants forming products. Again, in that process, our products contain less energy than our reactants did. So it has to give off the extra energy to the environment. So it's releasing energy to its surroundings, maybe the table it's sitting on, the glass container it's in, your hand if you touch the flask. All of those things are gaining the energy from the reaction. So quickly, another term that we typically use instead of energy is the term enthalpy. And enthalpy is the energy of a system that's contained in it. We use the symbol H for enthalpy, and we use delta H to signify the change in enthalpy, because usually we are looking at a change from maybe reactants to products, or a change in temperature, or a change in state of matter, all of those things. So a change in enthalpy is positive for endothermic reactions and processes, as the total energy is increasing. So we're going to get that positive change in energy. And it is negative for exothermic, as the total energy is decreasing. We're losing energy to the surroundings, so we're going to have a negative change in energy, or enthalpy. All right, taking a look more at endothermic reactions. So these are reactions that require more energy to be absorbed, excuse me, to break bonds than is released when bonds are formed, making it endothermic. With these, energy or heat is considered a reactant. So a good example of this is photosynthesis. So we've got 6 carbon dioxide and 6 water molecules plus energy. So we've got our carbon dioxide and water from the air and in our plant, and we add energy from the sun, and it creates the sugar and oxygen molecules, gives off oxygen. So this is endothermic because we can see the energy is part of the reactant side. So energy is taken in to break the carbon-oxygen and hydrogen-oxygen bonds within carbon dioxide and water. And any excess energy is released as the new bonds in C6H12 are formed, but more energy is required to break bonds than is released in the reaction. So we can see in an endothermic graph, we've got reactants, and then our products are always going to end higher than our reactants, and we are absorbing energy during that reaction. So our change in energy during the reaction, this amount in our chemical reaction, corresponds to this amount on the graph here, that energy absorbed, and it's going up, so it's positive and endothermic. So these reactions absorb energy from their surroundings. So energy is going into the system from the surroundings. Since they are absorbing energy, a thermometer will drop in temperature. And this right here is where I see a lot of students get confused. So let's think of it this way. If this circle, inside this circle is my system, my chemical reaction, a thermometer is not part of the chemical reaction. It is outside the system. So if my system is taking in energy from its surroundings, it's going to take energy from that thermometer as well if I stick a thermometer in my reaction. And therefore, my thermometer is going to lose energy and decrease in its temperature. So endothermic reactions will feel cold to the touch as it takes in your energy. So if my hand is out here, this is going to be the worst drawn hand ever. Actually, that's not terrible. If my hand is out here, it's going to take energy from my hand into the reaction and absorb it, because we've got to gain that energy. We got to bring up that energy to get to our products. Okay. We've also seen these graphs in the last unit on kinetics. In this one shows the activation energy. They're in red on the graph, but that delta H, that change in enthalpy, is between the reactants and products. And that's where we care about right now. Our last unit dealt more with the activation energy. Now we're dealing with the energy of the reaction. Now an exothermic reaction is going to be the opposite situation. So reactions that require less energy to be absorbed to break bonds than is released when bonds are formed is exothermic. So we are releasing energy when we form those bonds, and we're releasing more than we need to break bonds. So energy or heat is considered a product of the reaction. We can see that here. So a good example of this is combustion. CH4 plus oxygen, so methane and oxygen, form carbon dioxide and water. We've got our hydrocarbon, CH4, and that oxygen forming carbon dioxide and water. That is our basic structure of combustion reactions. All combustion reactions are basically burning something, so we're going to give off that extra energy as heat, as light. We got extra energy to produce here. So energy is taken in to break the carbon-hydrogen and oxygen-oxygen bonds, and any excess is released as the new bonds in carbon dioxide and water are formed. More energy is released than is absorbed to break the bonds. So again, we're seeing that the energy is released to the surroundings. Our reactants have more energy than our products, so we're seeing that drop in energy. So that is our delta H of our reaction. So again, we've got our system where our reaction's happening. We are giving off extra energy to the surroundings. So whatever's in the surroundings is going to feel that energy. So since they're releasing energy, a thermometer will rise in temperature. So if my energy coming out hits my thermometer, that thermometer feels that energy, gains it, and goes up in temperature. The reaction will feel warm to the touch. Again, if I put my hand out here, I can only draw it one way. Terrible. I'm going to feel that heat coming towards me, so it's going to feel warm or hot to the touch. So we feel a beaker, it feels hot. That means our reaction is exothermic. It's giving us heat. Again, in our energy profile over here, we've got that activation energy in red, but our products still end lower than our reactants, and we've got our delta H. Now we can see it dropping down, so it's going to be a negative value, negative delta H here, right? We are losing energy from our system, so it is negative. We can also talk about the change in energy during a solution formation. So when I want to dissolve something in water, so an ionic compound. Let's take sodium chloride. So if sodium chloride, NaCl, sorry, I'm not using my fancy pen, so it kind of looks janky, NaCl. So if that's my solute and I dissolve it in water, the first thing that's going to need to happen is some gaining in energy. So our solvent, our water, starts out with a certain amount of energy, and we can see here that the particles need to spread out. We need to break some intermolecular forces between our water molecules in order to make space for the sodium chloride ions. So first they're going to spread out. Well, to break intermolecular forces, we got to gain heat. Okay, so it's a gain in energy. Sodium chloride, similar. It's got those ionic bonds, holding those ions in their crystal structure. We got to separate some of those. Again, we got to gain some energy in order to do that. Now, if I mix those together, and I've got my particles all ready to intermingle, then when they start to form their attractions between these ions and water molecules, that forming of attractions releases energy, and we form our solution. Now, if we release more energy than we gained, then we're going to have a delta H that is less than 0. So we're going to have a negative value, negative delta H. Okay, so if we lose more energy than we gain. But on the right side over here, we can go through a similar process, separating our water, separating our ions in our ionic compound. We have our separated particles at the top, but if our solution we make, when we form those intermolecular forces between our water and our ions, when it releases energy, if it doesn't release too much energy, then delta H is greater than 0, and we get a positive delta H. So an exothermic, down at the bottom it says exothermic solution, so this is one that's going to feel hot. If you were in my honors chem class or Miss Clicks or a few of them last year, we did the hand warmer design challenge, where you were just trying to figure out which chemical, when dissolved in water, heated up the water the most. Those were all exothermic. Besides one of them, we did put one chemical in there that was endothermic and got cold. Hopefully you didn't pick that one as your hand warmer. But if it feels cold when you dissolve something in water, it's an endothermic solution formation. So they both have to go through the same process. It just depends on which one requires more energy So if it's endothermic, it's requiring more energy to break apart the ions in water, separate those intermolecular forces, than it is when they form attractions. Or if it's exothermic, then we are, again, requiring energy to separate the ions in the water molecules, but it's giving off a lot of energy when it forms the intermolecular forces. So that's what's going on with solution formation. They can still be endothermic or exothermic, just depending on how that energy changes within that process. So heat transfer. Heat will always flow from our substance or object that has a higher temperature to the one with lower temperature. So this helps us figure out the direction of heat flow and if something is endothermic or exothermic. The hotter, more energetic particles will collide with less energetic particles or colder ones and transfer the energy. So our hot particles, we can see in the picture, are vibrating more, those ones in red, and as they hit the ones in blue, they start to transfer that energy and those ones start to warm up and move faster. So this is how heat is actually transferred from one substance to another. We can imagine these particles shown in the animation here as air molecules, and that's how heat is transferred through the air from, say, a fire. So that's why you can put your hands a little further away, but you can still feel that heat. It's through the air. It's also through the radiation of the light, that infrared radiation coming to you as well. So that's how we conduct heat, though, through objects. The particles vibrate, they hit each other, they collide, and they transfer their energy. All right, the last thing is thermal equilibrium. So heat transfer again happens as the particles collide and transfer their energy from hot to cold. So heat transfer will continue to happen from hot to cold until the substances are at the same temperature. And this is called thermal equilibrium. So if I have a substance at 100 degrees and a substance at 0 degrees, the one that's hotter at 100 degrees, let's say Celsius, will give its energy, the particles will collide and transfer their energy to the one at 0 degrees Celsius until they are both the same temperature. Now in this example up here, if we have equal masses, let's say they're both 10-gram samples of water. So 10 grams of 100-degree water and 10 grams of 0-degree water, and we put them together, they're going to meet in the middle at 50 degrees because we have equal masses of the same chemical. Okay. Now, if they aren't the same mass, they will meet at a temperature closer to the one with more mass. So if they're both water, but one's 100 grams and the other one's 45 grams, the one that's 100 grams, whatever temperature it's starting at, we're going to end closer to that temperature. So if that's the hotter one, our final temperature is going to be warmer than halfway between. If it's the colder one, then it's going to be colder than halfway between. All right? So it shifts it a little bit. So your amount of energy that is exchanged between your substances, so this amount that's moving between the 100 degree and the 0 degree, depends both on the mass of the substance and the temperature of the substances, okay? So if your masses are different, that's going to change your amount of energy that's gained or released. If their temperatures are closer to each other, we're not going to exchange as much energy as if the temperatures were further from each other. So both of those have an effect on the amount of energy exchanged. So we're going to keep exploring energy, and the next part we're going to do some calculations, but this gives you a nice little intro to our energy, endo and exo, and graphs and thermal equilibrium. Thanks, guys.